All right, so we are going through Unit 10 here today. This will be kind of a quick little lecture on this. As we go, Unit 10 is all about dimensioning and tolerancing, gives you some familiarity on how this works. This is, of course, tied in the Ask Me Why 14.5. So, and of course, we've already talked a little bit about some of the math that needs to be done and used when we're figuring out some of these dimensions and tolerances. So, as we go through, everything in industry, of course, needs some type of dimension in order for it to work and function the way it is intended to. So you have a couple of examples here with some dimensions on some railroad track and what's kind of critical. And of course, if we do not meet those particular specifications, definitely in the case of this railroad track, we could have accidents occur, trains derail, parts and trains are damaged, people get hurt. So we need to be aware of dimensioning standards and how they get applied and how they convey design intent. So on most prints, a lot of times you might just be given a dimension but no actual tolerance. Just because it's only a dimension on there doesn't mean that there's still not some implied tolerances. So you always need to go through and make sure that you're looking at the title block of the print and seeing what the implied tolerances are based on the either 1, 2, or 3 place dimension. And of course, you've got fractional and angular tolerances there that would be that you would need to read and be aware of as well. So we do have a couple of different names for some of the tolerances that are applied. We've got what we refer to as a limit dimension, which you see up here in the upper left-hand side. We've got a bilateral or equal. Basically, the tolerance goes the same direction, so plus or minus in the same. We also have what's referred to as a unilateral dimension here. So where it's given to you as a plus 5/10 minus 0. Of course, that could also be the other way where it would be plus 0 minus 5/10, depending on what the design intent was with that as well. Although in most cases, we'll talk more about proper fits for pins and holes as we go through. And then there's also the bilateral unequal type tolerance here as well. Now, all of this, of course, is terminology that draftspeople and designers might be needing to be familiar with and talk about. To be honest with you, though, I don't know of a whole lot of machinists that are actually out there on the shop floor that are actually referring to these as a bilateral equal or bilateral unequal, unilateral, or are these actual names. At least not in my experience. Of course, if you're watching this video and your shop does constantly use these terms for this type of tolerancing method, leave me a note there in the actual messages here on the YouTube video and let me know. But in my 30 years, usually when I've been working on the shop floor, we just kind of refer to it as 1.5 plus or minus 2/10 or 1.5 plus 5/10 minus 0, whatever the actual tolerance on it was. All right. Now, there are in industry lots of what we refer to as nominal sizes, where as things are produced, we don't really think about the actual size. There's some generic terms, what they're made, called nominal size. The best indicator of this, of course, is on your lumber. When you're thinking about 2x4s or 2x6s, usually those don't actually measure 2x6 or 2x4. They actually measure about 1.5 by 3.5 or 1.5 by 5.5. And those are considered nominal sizes. It's just kind of industry jargon that has kind of developed over time that we use to refer to those particular boards and that type of lumber. We have the same thing when we talk about pipes different pipe schedules. So schedule 40, schedule 80, different pipes when we're talking about bricks. So, and then even our gauge sizes, there's also different gauge sizes over here that would also be kind of classified as a nominal size. And you'd get to read the chart and kind of get familiar if you're working in an industry where you're really using these type of units all the time and these type of drawings. All right, so what we really get into here as we go, so sorry about my mouse isn't quite cooperating with me. What we really get into is the way things fit together here. And we've already talked a few times in the classes about a clearance fit, a slip fit, or a press fit, what I usually refer to as a clearance, slip, or press. Some of the jargon, other industry jargon that you'll hear will refer to these as interference fits as well. So be aware that there's some differences in terminology there. And of course, wherever you're working at, you'll get used to that terminology here. But so what we're really getting into now is the relationship of shafts to holes and how we determine what the fit should be. So you give an example here of these sizes. All right, so here is a couple of other examples here. So, of course, we got a metric shaft going into a metric hole over there on the upper right-hand side. We've got a U.S. customary fit on the lower right, and, of course, another metric shaft and hole on the lower left. In the upper left-hand corner of this PowerPoint, we're seeing what they're calling the envelope principle and giving you the beginning of the understanding of LMC clearance and MMC clearance, or allowance, what we refer to as least material condition and maximum material condition. And as you take a look at these, you should notice that there's kind of some standards being applied here, i.e., take a look at the tolerances that are on the shafts versus the tolerances that are on the holes. What are the bigger tolerances? Well, as you think about that and as you're looking at those tolerances, the bigger tolerances are given to you on the actual hole size. And the shafts are the smaller size with that. Now, we'll talk more about when we're designing and when we're kind of making these types of components to fit together where we want that. Basically, this standardization is really related to whether companies are buying stocked parts. So if you think about different types of, if you were an actual product designer and making assemblies, you probably don't have the resources to design your own ball bearings or your own roller bearings. You probably don't have the resources to design and cut your own gears. So there are these different fits, and you're probably going to outsource or buy those from some other manufacturers that specialize in gear making or specialize in ball bearing making. And so with that in mind, oftentimes the designer or the engineer that's going through this has to design these parts that would fit according to the bearing or the either the bearing or the actual gear that would be selected for that application. And of course, if the designer it's a large enough company where you're designing and able to cut both your own gears and make your own ball bearings and your own shafts and stuff, then you have a little bit more liberty as far as how you tolerance these parts and what becomes important to you in that design. All right, so here's some possible conditions that we can have on pins. So this is important to kind of take a look at. So of course we can have on the upper left-hand side here, we can have a totally straight pin here with the size and a totally straight hole. And we've got best of both worlds in that case and scenario. So that would definitely fit real easy. But we also get bit pins sometimes. So we have these other conditions where we have a bit pin, maybe we have a tapered pin, maybe we have this concave. I don't remember if that would be called concave or convex. Anyway, that type of shape there. And because of that actual shape, it may cause problems when it's trying to go into the hole. So we really are sitting there and we're going to kind of have to consider that when we make these. And this is part of the concept between your least material condition and your maximum material condition, making sure that even if that pin is tapered or bent or concave, that it will still fit in the hole that you need to put it in. All right, so here's some of our actual callouts that you can see here with this. This is our feature control frame, so just to give you some idea. So, and you do want to kind of get to know what each of these symbols mean. So, of course, that's our geometric tolerance symbol. Stop and think, what does that symbol mean? So I'll give you a few minutes and then we'll come back to it. So, of course, we've already talked about this is our diameter symbol. You've got a tolerance value. In this case, it's calling the maximum material condition modifier. You've got a projected tolerance symbol, a projected feature length, and then, of course, it's going to reference whatever datum that needs to be applied to. In this case, it's showing that it needs to be applied to all three datums, although it may only be one datum or two, depending on what the actual hole is. So usually it's probably going to be two. So if you think about it, if this is just like a flat plate, of course, we are going to want to have a datum for both sides or both side walls of the plate, and then of course another datum for the overall thickness of the plate, and that would give us a relationship with A, B, and C there where we spell out the datum. Another way that you can see it again is the geometric characteristic shown, and in this case, if you don't remember, I didn't mention it up here, but that's our true position. Again, you've got the diameter here as we go, your feature tolerance value, so your projected tolerance zone symbol, so your modifier, again, this is a maximum material condition modifier, the height of the projected tolerance zone, and again, your datum here as well. And this just gives you a little bit of a additional view of what these symbols mean. So your diameter, a spherical diameter, maximum material condition, least material condition, your projected tolerance zone, free state, tangent plane, statistical tolerance there. So are some of these things that you will see in some of the symbols you'll see on prints. All right, here's another example here where we're calling out datum A, and in this case, they're showing datum A as the actual diameter of this 10, I'm going to assume that that's a 10 millimeter hole, plus or minus 0.1, and they want that to be perpendicular within 2/10 there as far as B. So, and you see the call out here again, your feature control frame, and that's referencing datum A. So notice how it's spelled out, a couple of the different ways that they're kind of showing it here. So again, while a lot of times there's some standardization, this probably isn't the right way over here on the left hand side. Typically, you're probably going to see it a little differently, but depending on who the designers are and whether they're actually following the GD&T standard will kind of play a lot on whether that's actually spelled out correctly or not. All right, here's another example where this really comes into play and where we really got to know what our datum is. Now, in this case, they're showing this as a datum. So that means they want that plane is more important than this plane up here. So we would need to reference off of that plane and make sure that that doesn't move or that that fits within that tolerance zone. So, and you can kind of see how this is. Now, in general, we typically like to go off of greater surface areas because it gives us more stability and more rigidity when we're checking this. But for whatever the purpose of this part is, they're saying that that is not the design intent on this and that that's not included. So you don't want to go off of that longer side here. They want to make sure that you're going off of the shorter side. And you can kind of see this is good demonstration here, or good picture image that shows you how some of these things could be changed depending on how you're inspecting it and how you're confirming those tolerances. Another part here when we're talking about cones or angularity, the same type of thing here, especially with our roller bearings or ball bearings. You kind of see some tolerance zones there. So this was a good one to show you how this might be applied. So, and how we might get some different radial movement in ball bearings to make sure. Of course, the looser that ball bearing is, the more chance that that's probably going to prematurely wear out. And we're going to have to replace it more often. So this is the other aspect of applying some of these tolerances. The closer that we can get a good tolerance, and the better we can get it at true shape, the better and the longer that part is actually going to last in actual runtime for whatever the use of it is for. All right, some more angularity here, and we're talking about some different types of tapers, taper gauges, so you guys can take a look at that and how those are applied. So we'll come back a little bit more and talk some more about that in class. And this is a Morse taper, so this is pretty common on a lot of your manual milling machines to have these Morse tapers. And again, you're looking and seeing all these different charts that kind of spell out what the taper is and what the size would be related to. So if you're machining or making these, you'd be consulting these charts to make sure that you're following them and making them the way that they need to be made. A controlled radius tolerance. Oftentimes, if we're checking with radius gauges, most of the time, a lot of the times, radiuses are put on for lead in or just to allow for a smooth run over a part. Sometimes, however, they are much, much more critical and require a close to exact radius size as possible. And we spell that out with what we refer to as the controlled radius tolerance. This shows you a couple of examples of how that radius tolerance would be applied on a print as well. All right. Here is another example. You see the radius 3 max. Now, in this case, this is not a controlled radius. It's not spelled out as so much. So we have a little bit more clearance. We would probably want to refer back to the implied tolerances to see what that is. But what we do need to make sure that we hold is it says 3 is the largest size that radius can be. That's what that 3 max means. So we would not, if we made that radius larger than 3.0, the part would be scrapped and could potentially be kicked out and have to be remade. Some additional tolerance zones here as we really start to spell these out. So you're going to really kind of need to get to know what all of these symbols mean. And again, you can kind of take a look at some of the variables here with our upper control limits, lower control limits. Again, this is a lot of this is going to be, if you are in the inspection room and inspection department, you're definitely going to be paying a lot of more attention to this. If you were working on the machine shop floor, then you're probably going to be paying a little bit more to actual fits as opposed to kind of developing these charts. But your quality control department is definitely going to be one to make some of these charts to make sure that they can give those reports to the customer. So just some more examples of different types of fits on cylinders. So again, how things could be bent or formed. If we're talking about radial things here, this is probably if you're imagining a tool change situation, these angles and some of the true positions for that tool changer to work has to be pretty accurate in order for it to be able to pick up the tool changer and move it and put it in the spindle the right way. And there's a lot of accuracy that has to be implied with that and conveyed on the design intent. So now we're back to these shafts and the least material clearance, maximum material clearance. So again, with these, we talk about different types of clearance fits, and you're going to have charts that you're going to read to make up on these. So here's a example of one of those charts that you would read. And you can see how it's broken up into different classes: a class RC1, a class RC2, a class RC3, class RC4. And when we're talking about the size, so you'll see the nominal size range over here. So you will come down and you'll kind of find where your size falls in. Now, this is inches, so this is US customary system. So, for example, if we had a 5/8 pin, we would come down here, and 5/8 measures 0.625. So it's going to be here at this one. So we would then kind of come over and read through the chart depending on which class of fit we would want. And then we would apply that to both the hole and the shaft once we calculated and did that basic math. So your assignment then for today is to review activity 10.1. So you're going to see we've got the maximum material conditions, your least material conditions, both on the holes and the shafts, and you've got some allowance. So go back through. There's a couple of other examples in the textbook that you can kind of look. Try to figure out, again, so this is saying this is a 5/8 basic size, and they're wanting this to be an RC3 fit. So you'll have to go back to that chart and look to see where that falls and basically put those limit sizes there. Same thing here. This is a 1.5. They want that to be an RC2. A 1/4 RC3, 2 3/8 RC1, and a 1-inch that's an RC2. So then you can kind of come back in here and fill out that chart with your calculations to see what the hole size limits should be and what the shaft size limits should be as well. So that's going to pretty much end this lecture. So if you have any questions,